It's an unnatural sight. A Boeing 747, the queen of the skies, an icon of global travel, that has carried millions of souls across ocean, now sits motionless under a harsh desert sun. Its engines, 4 massive powerhouses that once defied gravity, are gone. Gaping holes remain where they once hung. Soon, a giant hydraulic shear, looking like a prehistoric predator, will approach its wing. There won't be a ceremony, just a metallic crunch that echoes across the tarmac, signalling the end of a 30-year career. This isn't a slow, mournful decay. This is a high-stakes, precision-engineered race against time. The industry average to fully dismantle and part out a jumbo jet used to be 2 to 3 months. Today, specialized facilities
timeline has been
can do
drastically
it
reduced.
in
We
as
now
little
have
as
exactly
12
days remaining.
This isn't just faster, it's a revolutionary leap in efficiency. But how? How do you take a 400-ton, 6 million part puzzle box built to withstand the most extreme forces imaginable and systematically unbuild it in less time than a family vacation? The answer isn't brute force. It's not a chaotic demolition. What you're about to see is one of the most sophisticated, unseen, and consequential engineering operations in the world. This is the story of how we take apart the giants of the sky, and in doing so, reveal the future of how we build them. It's a story of incredible tools, vast digital networks, and a fundamental flaw that could ground the promise of a truly sustainable aviation industry. First, we need to correct a common misconception. When we think of retired aircraft, we picture boneyards, vast, dusty fields in Arizona or California, where planes are left to bake in the sun. It's a romantic, yet deeply misleading image. These facilities are not graveyards. They are highly active, multi-billion-dollar working industrial hubs. They are the final, and arguably one of the most critical, stages in an aircraft's life cycle. An out-of-service Airbus A380 or Boeing 777 isn't a piece of trash. It's a treasure chest. Up to 90% of its components, by weight, can be recycled or reused. We're talking about engines worth billions, landing gear assemblies in avionics, hydraulic actuators, and even interior components like seats and galleys. The raw aluminum in its fuselage alone is worth a small fortune. These aren't just spare parts, they are certified, flight-ready components that keep the global fleet of active aircraft flying safely and affordably. The economic imperative is relentless. A grounded aircraft is a non-performing asset. For the recycling company, every day a plane sits on their tarmac. It's costing them money and space and opportunity. For the airline that sold it, the speed of this process determines how quickly they recoup their investment. This pressure, this need for speed, created a powerful incentive to innovate, to transform the slow, manual labour of the past into the hyper-efficient, demanufacturing process of today. So, let's get to the first revelation. A 70% reduction in disassembly time. How? This leap isn't just about working faster, it's about working smarter, with tools that exist nowhere else on Earth.
Activating the cutting sequence
The
now.
process
The orange
begins
lines indicate the
not with a
precise
wrench,
trajectory for the plasma
but with
torch.
a plan.
Confirmed.
A team
Structural
of
integrity
engineers
holds.
digitally models the entire deconstruction, sequencing every single cut and removal to maximize value. The goal is surgical extraction, not demolition. The first step is to depollute the aircraft. Every fluid, jet fuel, hydraulic oil, coolant, even water from the lavatories is meticulously drained. This is a critical environmental door and safety step. Only then does the heavy equipment move in. But these are not your standard construction tools. Take the hydraulic shears. They are custom designed with specific jaw shapes that match the cross-section of an aircraft's body, allowing them to cut precisely without crushing nearby hydraulic lines or wiring looms that are slated for salvage. Then there's the challenge of the rivets, hundreds of thousands of them. Manually drilling out each one would take months. Instead, teams use automated rivet removal tools that can precisely locate, drill, and extract a rivet in seconds. For delicate composite panels, lasers are the tool of choice. A laser guidance system maps the panel and directs a high-energy beam to slice through the epoxy resin, allowing the multi-million-dollar panel to be removed intact without microfractures. This suite of specialized equipment transforms the airframe into a kit of parts. Engines are removed with custom cradles. The landing gear is dropped using hydraulic jigs. Even the wiring, miles and miles of it, is extracted by machines that pull entire looms through the fuselage. Every action is optimized for speed and for the preservation of value. Now, if the physical disassembly is impressive, the digital infrastructure behind it is arguably more so. A single Boeing 747 can have over 12,000 components that are candidates for reuse. How do you track them all? And how do you prove to a buyer, and more importantly to the FAA, that this specific actuator from a 25-year-old plane is safe to install on a 15-year-old plane currently flying passengers? The answer lies in managing the aircraft's digital ghost. Every single component removed is immediately tagged. This isn't just a simple barcode. Increasingly, it's an RFID tag that links the physical part to its entire life story in a massive database. This database contains its original serial number, its full maintenance history, flight hours, cycles, and any repairs. Without this data, $1 million engine part is worth only its weight in scrap metal. This is where next generation technology comes in. Some firms are now using blockchain to create an immutable, unhackable ledger for high value components. When a part is harvested, its data is entered. When it's inspected, certified, and sold, each transaction is a new block in the chain. This provides an unprecedented level of trust. You can combating the persistent problem of counterfeit parts in the aviation industry. Furthermore, machine vision and AI are revolutionizing the inspection process in a hacked time. High-resolution cameras scan components for microscopic stress fractures. AI algorithms trained on vast datasets can flag potential issues that a human inspector might miss. This digital ecosystem doesn't just manage the scale of 12,000 parts. It underwrites the safety and economic viability of the entire recycling industry. It's what turns a boneyard into a bank. For all this incredible progress, there is a dark spot on the industry's X-ray. A deep structural problem that gets bigger with every new plane that rolls off the assembly line. While we have become masters at recycling aluminum, we are failing miserably with the materials of the future, composites. Modern aircraft like the Boeing 787 and Airbus A350 are not primarily metal. They are up to 50% composite materials by weight, chief among carbon fibre reinforced polymer, or CFRP. This material is a miracle of engineering. Stronger than steel, lighter than aluminum. It's what makes these new planes so fuel efficient. But it has an Achilles heel. It's incredibly difficult to recycle. The problem is in its name. It's a composite. It's not a pure element you can just melt down. CFRP is made of super strong carbon fibres, suspended in a rock-hard epoxy resin. To recycle it, you have to somehow separate the valuable fibres from the worthless resin. And, as a result, today, a staggering 95% of composite material from decommissioned air ends up and gets shredded. The miracle material then becomes a permanent piece of trash. This is the paradox of modern aviation. The very material that makes planes greener in the air makes them a potential environmental disaster on the ground. And as thousands of first-generation composite aircraft approach their retirement age, we are facing a literal mountain of a problem. A mountain of unshreddable, unmeltable wings and fuselages. So what's the solution? Researchers are racing to find two primary technologies show promise: pyrolysis and solvolysis.
The CFRP enters the furnace where the intense heat causes the purple resin to vaporize.
Burns off
this process, known as pyrolysis,
leaves the carbon fibers behind. The problem? This intense heat can damage the fibers, reducing their strength. They get downcycled into things like laptop cases or car parts. Solvolysis. That's the more elegant approach. It uses specialized solvents at high temperatures to dissolve the resin, leaving the carbon fibers almost perfectly intact. This is the holy grail, recovering fibers pristine enough to be reused in new aircraft, effectively closing the loop. But scaling this from the lab to an industrial level, cost effectively, well, that remains a massive engineering hurdle. The 12-day teardown, therefore, represents a brilliant yet incomplete victory. It's a masterclass in logistics and mechanical engineering, but it also highlights our failure to plan for the entire lifespan of the materials we create. The future of sustainable aviation doesn't just depend on more efficient engines. It depends on answering this fundamental question: how do we design for disassembly? The next great leap in aerospace engineering might not be a hypersonic jet, but an aircraft whose every component, from its aluminum ribs to its carbon fibre wings, is designed from day one with its end of life in mind. A plane built not just to fly, but to be taken apart, with every material destined for a new life. Until then, the clock will keep ticking. Not just on the 12-day teardown of old jets, but on our chance to build a truly circular sky. The monumental task of unbuilding a titan of the sky begins with a single, calculated cut. Precision is paramount. Every salvaged component is a victory against waste. The digital ghost of the aircraft awakens. Its history, now the key to its future, value. The carbon fiber paradox, a material born of incredible strength, presents a formidable, brittle problem for the future. The race is on, not for speed in the air, but for a breakthrough on the ground. The final frontier isn't space, but a closed loop. It's a sky that endlessly renews itself.